Hello and welcome to this lecture on multi-party Garbling circuit-based protocols. The talk will consist of three main parts. In the first one, we are going to describe multi-party garbling, in particular what a Garbling circuit looks like. In the second one, we are going to see how a Garbling circuit is evaluated, and all in the last one we explain a way to actually generate a Garbling circuit in the multi-party setting. However, since we are going to describe an MPC protocol, first we need to fix the setting, the MPC settings. So this means that we need to fix what kind of corruptions, we need to fix what kind of security we want, so how many, what kind of corruption the protocol is going to tolerate, and so on and so forth. So let's start with the MPC setting, and more precisely, let's start with a few remarks. The first one is that Garbling circuit-based protocols are based on a representation of the function that we want to evaluate as a Boolean circuit. So as an input, we have a Boolean circuit that represents the function that we want to evaluate. The second remark is that the protocol that we are going to introduce is different from secret sharing-based protocols, like for example speeds, that requires interaction between parties for each multiplication gate. It's different because the protocol that we are going to introduce only requires a constant number of rounds, and this number is independent of the circuit size and is actually very low. We will discuss this point at the end, perhaps in the last video. So we have a constant number of rounds. We are in the multi-party setting, so typically we assume more than two parties, say n, where n is bigger than 2. And our setting, our security setting is a dishonest majority with active corruptions. So this means that we can have up to n-1 corruptions, and the adversary can arbitrarily deviate from the protocol. It is well known that in this setting, so with dishonest majority, with a dishonest majority, we cannot achieve unconditional security. And in practice, here, this means that we need public key crypto that we know to be inherently inefficient. So this is one consequence, and the other one is that we cannot have a guaranteed output delivery. So the protocol that we are going to describe only achieves security with a board. So this is the security we can, this is the kind of security we can hope for. What about efficiency? Typically, the public key machinery needed to define an MPC protocol in this setting, so with a dishonest majority and malicious adversary, is very expensive. And one very common solution to achieve efficiency is to design the MPC protocol in the so-called preprocessing mode. This is something that we already saw in a previous video about secret sharing-based protocol, like speeds. Okay. So we can have a preprocessing phase, and in this first part of the talk we assume the existence of a trusted dealer, which doesn't need to know the actual input of the computation, but only the function that needs to be evaluated. And this trusted dealer will supply the Garbling circuit, so a kind of an encryption of the circuit that the parties will evaluate in the online computation. So as in secret sharing based protocols, we have two phases, a preprocessing phase and an online phase. However, compared to those protocols, so protocol based on secret sharing schemes, we have two main differences. The first one is that in the preprocessing phase, the trusted dealer needs to know the function to be evaluated. While in secret sharing based protocols, this is not required. So secret sharing based protocol, the preprocessing phase of secret sharing based protocol can be both function and input independent. The other difference is that in secret sharing based protocol, the online phase can be information theoretic, and this is not the case here, and this is something that is also true for the two-party case. So okay, we have two phases, and very high level, the protocol will work as follows. We have a Boolean circuit C as input, and we will have a Garbler phase that produces CT. That's why garbled version of the circuit C. Then given the inputs x1, xm, we have input encoding phase that produce an encoding of the input, and given the garbled circuit and the encoding of the input, the parties can evaluate the circuit essentially without interaction. So this is a very high level of multi-party garbling. However, what protocol are we going to describe exactly? The first multi-party garble circuit based protocol was described in 1990 by Beaver, Micali, and Rogaway. They presented the so-called BMR protocol, that is a generalization of Yahoo's approach to the multi-party setting. But the protocol that we are going to describe is a modification of the original BMR protocol, and it is strongly based on these two works. BLO16, that gives a very efficient BMR style protocol for semi-honest adversaries. And the description of the garbled system that we are going to see in this talk is exactly the one given in this paper. And then the other paper that we are going to on which this talk is based is the paper by Azai et al. that shows a modification of BLO to achieve active security. And one nice feature of this protocol is that once the garbled circuit is correctly generated, the online phase is actively secure, essentially for free. So the overhead compared to the passive variant of the protocol is very low for the online phase. So this concludes the first video on BMR.